All right. Do need to collect a little bit of data before we get going here. So those of you at home, if you would just send back to me something kind of like this. It just needs to be your gender and then whether you prefer math or English. And no hard feelings. So just send that back to me. Toot sweet. Mason? Aiden? Jordan? Caleb? Brian? Sam? All right. All right, make people here. Doo-ba-doo-doo. All right. Dion, see, Dion. I knew she wouldn't answer. Oh, there she is. All right. Okay. All right. Here's our class data. So just like yesterday, we need to total the rows, total the columns. Okay. Aiden, why do I get the feeling you're hiding something back there? So why do I get the feeling you're hiding something back there? Get up to the toilet, man. All right, what else do we need to do besides total the rows and total the columns? Okay. So what's that altogether? 12. Go.
Safe to assume that intelligence.
Mayhaps. All right, so what group of people, so yesterday, we compared like Facebook and Twitter, to those circles. Today we're looking at the groups of females and the group of people that preferred English. Okay, so we're comparing the group of females to the group of people that prefer English. So what group of people does this represent? I'm not asking for a number here. I'm asking for what group of people does this represent? Does that space represent? Females, yeah, right. Same, females who prefer English. So how many females preferred English?
4.
Okay. What group of people does this represent?
4 male.
All right, so yeah, it's the groups that was male and preferred math, or the groups that were not female, aka male, and didn't prefer English, aka preferred math. So, yeah, so the not female, not English group would be on the outside there. And how many males preferred math?
4.
Also 4. Okay. Slow down. What group of people does this represent?
Females. Total is total.
Not total amount of females. Total amount of females would be the whole circle. So what group does this represent? So whole circle is females. What group is this? Females that prefer math, right? Females that do not prefer English. So females that prefer math. So how many is that? 1. Okay. And the last question here. What group of people does this represent? Okay, so not females that prefer English, right? So How many males preferred English? Okay. So again, just kind of focusing on like where does that data come from? What group of people or whatever is being represented by each piece of the Venn diagram? Okay, where is each section? What does it represent? It's not just focusing on the numbers, but describing the group of people or whatever we're talking about that's being represented there. So, okay. So using our class data, if we were just to randomly select a student, what would be the probability that the person is female?
5 out of 12.
5 out of 12? Where'd you get that number from, Mason?
I got that I got the total. Never mind.
I'm not saying you're wrong, I'm just asking a question.
Yeah, total.
Okay, so there's 5 females out of 12 people, right? So, so that came from right there. Okay. What's the probability that a student chosen at random would prefer English? So we're getting that 7 out of 12 from Mason. Okay, so the total of the English column, okay, so 7 out of 12. So I know we have a different way of saying this, right? The probability of, I would usually say not female, not no female, but we could say, it's the probability of being male, but again, this idea that this would be the complement to being female. So we've talked about that the other day, the complement of the probability. And I know we have a very small data set, so it's easy to look at the people who aren't female, so the people are male and just see their number. But I'd like to make sure you guys remember that how you find the complement is you take 1 minus whatever they're talking about. Okay, so to find the complement of a probability, you take 1 minus, and then you take 1 minus the 5 out of 12. So the probability of not being female would be 1 minus 5 out of 12, which of course is 7 out of 12. So and we can see that it matches what we think it should be. Okay, again, just making sure you guys remember how to find the complement of something. So what's the complement? What's the probability of the complement of English? Right, not preferring English. Again, 1 minus the 7 out of 12. Which would give us 5/12, which again we can see matches how many people said they preferred math. Okay. So with a much larger set of data, finding the complement this way would be easier. You'd have a lot more stuff to look at and try to figure out. Since we have a very small set of data, it seems very easy to do it a different way, which can hide things from you and hide methods from you. So what about the probability of being female and preferring English? We talked about the word "and" yesterday, how that where that comes from. So it's about the probability of being female and preferring English. Where would we find that? Okay. What about over here in, where would we find that? Yeah, find it in the middle of the Venn diagram. So we're looking at the overlap of those two groups. Okay. So we had 4 students that were female and preferred English. So the middle of that Venn diagram. And I know 4 out of 12 can be reduced, but I don't want to reduce that. I just want to keep everything with the same denominator so it's a little bit easier to compare. Okay. Normally I would say reduce that, but I just want to keep everything in 12s for right now. What about, where on the Venn diagram would this be? The probability of English and not female. Where would this be on the Venn diagram? On the right? What do you mean? Over here? Blue, right? So in the English group, but not in the female group. So in the blue, so probability of preferring English and not being female, what is this blue section? So that'd be the 3 out of 12. And I'm choosing not to reduce that. I don't know anybody from Florida. What about the probability of being female and not preferring English? Where would we find that on the Venn diagram? Probability of being female and not preferring English. So where's that on the Venn diagram? So that green part here. Okay, so the group that's in the females but not in the English group. So 1 out of 12. And the last one, where on the Venn diagram would we find the probability, those that have probability of not being female and not preferring English? Where in the Venn diagram would this be? Okay, very outside. Yeah. So not in the female group, not in the English group, so on the outside of the Venn diagram. So you have the purple, so 4 out of 12. So again, just kind of seeing how the Venn diagram represents those two things. So the probability of English, preferring English would be the total that's inside that English circle. The probability of being female would be the total that's inside the female circle, so the 1 plus the 4, right? The 4 plus the 3. So the probability of not being female, so what's the total that's on the outside of the female circle? 7, the 3, and the 4. It's the probability of not preferring English. So what's the total that's not in the English circle? So the 1 and the 4. That's where we get our 5. And so how does the Venn diagram relate back to these things here? Okay. And then yesterday and on Friday, we talked about this word or. We start saying the probability of something or something else. What do we do with our probabilities? We add them, right? So that word or started saying, hey, we should add those probabilities. So the probability of being female was 5 out of 12. Probability of preferring English, 7 out of 12. So the probability of being female or preferring English should be 12 out of 12. So everybody was female or preferred English? So we have to take out the people that preferred English and were also female, right?
Yeah.
So because some people were what?
You're to like pick it out of the bag, right? You have a 100% chance of picking someone that has that other like switch.
Yeah, so what's happened here? Why does that math seem bad? What's happened? Kill?
They doubled up.
Yeah, some people doubled up, right? Some people got double counted.
Yeah, that's why I was saying that you should take out people who prefer English.
Yep. So we need to take out the people that preferred English and female, right? Because what's that mean about these events? That some people got doubled up. So that means these events are not mutually exclusive, right? So mutually exclusive events can't happen at the same time. So these events are happening at the same time. So these are not mutually exclusive. So we have to make sure this math doesn't work, right? So when we see that crossover in the Venn diagram, that section in the middle saying, hey, there's going to be some people that are double counted. So to find that, to do that math, we'd have to take the probability of being female, which was the 5 out of 12. And then we'd want to add the probability of being or preferring English, which was the 7 out of 12. But then we subtract, so Aiden said we need to take out those people who are double counted. So the probability of being female and preferring English. And again, that's that piece that's in the middle there. So there's 4 people that were female and preferred English, so they got double counted. So we need to take them out once. So they go in twice, but then they get taken out once. So they're either still in the 5 out of 12 or they're still in the 7 out of 12, but now they're not in both. So 5 plus 7 is 12, minus 4 would be 8. So watching out for that idea of events being mutually exclusive or not. Again, mutually exclusive means that if the events are mutually exclusive, they cannot happen at the same time. If I'm rolling a die, I can't roll a 3 and an even number at the same time. If I'm picking marble out of a bag, I can't pick a blue marble and a red marble at the same time if I'm only drawing one marble. Okay. I'm drawing a card out of a deck. I can't draw a face card and a 7 at the same time. Those things are mutually exclusive. If I say I draw a face card or a heart, then all of a sudden there's crossover there. Some things are going to get double counted. So all that stuff that we just talked about up through 3 was all stuff we've talked about, yesterday and Friday. Is there still anything there with that kind of older ideas you guys want to clear up before we move on to the new ideas for today?
P and no female.
Oh, here. So when we say like the probability of being female and then the probability of not being female, so again, I prefer to say not female versus no female. That's called the complement. Okay. So if I say what's the probability, if I'm looking at rolling a die, so I can say what's the probability of rolling a 2, right? It'd be 1 out of 6. If I say what's the probability of not rolling a 2, how many ways are there to not roll a 2? Well, there's 5 ways that aren't 2 out of the 6. Okay. The complement and the event itself would always have to add up to 1. So if I know the probability of the event, I could find the probability of its complement by subtracting it from 1. Like this is essentially like 100%. Okay? So 100% minus whatever percent this is would be, whatever fills up the rest of the 100. So if I told you that there was like a 13% probability that it's going to rain today, I say, what's the probability that it's not going to rain? You would say 1 minus 13%, right? So you could say, well, it's an 87% chance that it's not going to rain. Okay? That's called the complement of the event. Anything else from the old stuff before we look at this idea of if events are independent or not? We have a new idea for independent events. Okay, so there is some notation we need to get down before we deal with the math side of it. So when we say what's the probability that a student prefers English given that they are female, how do we write that in this notation? Okay. So the notation for that would be P of English, and then you just use a vertical bar. Sometimes I turn it into a slash because we're going to make a fraction, but really it's like a vertical bar. It's like half of a absolute value. Okay? So it's just separating them. P of English given, so you don't use the word, that basically stands for the word given. Given female. Okay? So how I would read this would be the probability of someone preferring English given that they are female. Okay? So basically this here says all of this. Okay? So this is just the notation we use to stand for this whole sentence. So this vertical bar basically stands for the words or phrase given that. So the probability that someone prefers English given that they are female. And the way we figure that out, so here's kind of the formula for it. It's the probability of both events occurring, both events occur, divided by the probability of the given event occurring. So the probability of both events occur divided by the probability that the given event occurs. That's how you figure out the probability of one thing given another. So you need to make sure you're paying attention to the reading, like which event is being given, which one isn't. So when you read this, it says the probability that a student prefers English given that they are female. That's telling us that's what needs to go in the bottom. Yeah, so if I start there, so it turns out that we don't need the full probability when we do this. We just need the numerators. Okay? I'm not going to explain to you guys mathematically why that is, but I just need basically the number of times that the numerator of the probability that they're female. So how many out of our 12 students were female? 5. Okay. Here, the probability that both events occurred. So the probability of someone being preferring English and being female. What was the probability of someone preferring English and being female? 4. Yeah, 4 out of 12. Right, that was up here. So we're taking the probability of being female and comparing it to the probability of being female and preferring English. I'm grabbing this 4 right here. And we're going to turn that into a percent. So 4/5 is a percent is what? 80%? Okay. So yeah, there's a mathematical reason why we don't need the 12s. And if you guys are really curious about that, I can tell you that. But we can just use the numerators. We don't need the full fractions for those probabilities. Okay? So there's our probability that someone prefers English given that they are female. Next question says, what's the probability that a student prefers English given that they are male? Again, how I would write that in the notation, it would be P of English, then that vertical bar, given that they're male. Again, that's the probability of both happening divided by the probability of the given happening. I like to start with the bottom, the given part. It doesn't matter. So what's the probability of the student being male for this class? 7 out of 12. Okay, so we just need the 7. Okay. What was the probability of the student being male and preferring English? 3 out of 12. Okay. So that 3 came from English and no female, right? It's this 3 right there. And what's 3 divided by 7? %? 40.8. Thanks, Mason. So 42.9%. So we have the probability of student preferring English given that they're female, with the probability of a student preferring English given that they're male. And we're asking, are the events of being female and preferring English independent? Are they linked? Does one have an effect on the other? So this idea of independence, right? when I think about rolling a die, the die doesn't know what happened the last time I rolled it. I can roll a 3, and I roll the die doesn't know I just rolled a 3, so it's like, well, I better not roll a 3 this time. So last time I rolled a 3, so this time I'm going to roll like a 4 or a 5 or a 2 or something like that. It doesn't know that. Each roll would be independent of it. Right? If I flip a coin doesn't know what it landed on last time. So the next flip is going to be independent. The first problem set you guys did for this unit was talked about a train being on time 90% of the time. The train doesn't know if it was on time the day before, saying, well, I was on time the last 5 days, so I'll be late today. It doesn't know that. That's an independent event. Are these things linked, right? If they weren't linked, if being female didn't have an effect on preferring English or not, what would we expect to see from these numbers? If being female didn't have a link to preferring English, what would we expect to see from these numbers? I don't think you're hearing my question, Nathan. If being female didn't have an effect on preferring English, what would we expect to see from these numbers? If there wasn't a link between being female and preferring English, what would we expect to see? They should be the same. So if being female didn't change your chances of liking English, that means that it should be the same as being male and liking English. Those should be the same. But they're quite obviously not the same. So are they independent? Not. If they were independent, then they would be the same. All right. So our data shows that there is a link between being female and preferring English. That if you are female, there's a much higher chance you're going to prefer English to math. That's what the data shows. Right? Obviously, that's just data for our class. Can't say that. We can't take that and say, well, this is how it is for everybody. But maybe we could take that class and say, students in the school, maybe, right? Yeah, but when they take samples for people in, like when they talk about statistics, polls and stuff like that, they're trying to pull thousands of people. Even there, it's just taking thousands of people and then saying that's what America's like. It's still pretty crazy. But there is a way to set that. I don't know enough about statistics to say, like, here's how many people you should poll in order to say this is what America's like. There is a way to calculate that. But statistics is specialized enough that I don't know how to figure that out. So I'm saying our data shows that if a student is female, there's a much higher chance they will prefer English to math. I mean, it's almost double. So these are dependent events. Not independent, they're dependent. That's the way it's been in every class. I think you guys had the widest margin, but it went from 25% to this is like 37%, and the other one was like 33%. So every class has been like this, as far as the obvious difference between males preferring English and females preferring English. Which is good. It's nice that it's obvious. And and there is a way, again, something I don't know, because I haven't studied statistics enough, but what would be called a statistically significant difference. We'd expect them to be the same, but if one was 80%, the other one was 79%, you wouldn't say that's a big enough change there to say that there's a link. So they don't have to be exactly the same. There is a small margin you're allowed to fall in, but again, that would be calculated based off of some stuff, and I just haven't studied statistics enough to know that. So, but there is a way to tell if things are close enough to say that, or if they're far apart enough to say that. So it's really not very much. I know that it can be like as little as like 5% change is enough sometimes to say, yeah, there's a link here or not. So I'm going to flip this over to you guys, start summarizing some things. Make sure you guys, if you have any questions, if something's not sitting right, that you're speaking up. If there's something else you want me to go back over. So we just talked about dependent events. There's a different way of saying that, which is just called conditional probability. So it's kind of just two words for the same, or two phrases for the same thing. Dependent events, conditional probability. That condition that the person was female had to be met first before we could say, yeah, there's a connection to the them preferring English. So it was conditional on them being female, and then saying yes, then they would more likely prefer English. Yes, that's called conditional probability. So that'd be P of A given B. Again, that's just like a vertical bar. Okay. And remember, A and B just stand for some event. Probability of preferring English given you're female. Probability of being male given you have blue eyes. Probability of having a Twitter given that you're female. Okay. All the things we talked about. So A and B are just stand-ins for some event. How we say this, so how do you read that notation? So that's the probability of A given that B occurs. Okay? So if B happens, the probability that A will also happen. Okay? If they're female, what's the probability that they're preferring English? If they're male, what's the probability that they have blue eyes? We could go back and look at our data from the second day and figure that out. Or second day, yeah. So the formula for that, how do you calculate that conditional probability? I'll give you a couple different ways to write it. So the probability both occur. Divided by the probability of that the given occurs. Again, there you got to make sure you read thoroughly, make sure you know which one's the given. Or another way to say that would be probability of A and B divided by the probability of B. And again, all you need there are the numerators on the probabilities. You do not need the denominators. And again, if you're curious, I can show you why that is mathematically. The denominators don't matter. And last thing was this idea of, what does it mean for our events to be independent? So knowing the outcome knowing the outcome of one doesn't change the probability of the other. I think I told you guys about this yesterday, but that idea of what's called the better's fallacy, that if you're playing something like roulette where it's just like red and black, if you're watching the game and you see that the marbles landed on a red number 5 times in a row, like, all right, it's got to hit black on the next one. Like, it's time, or it's due. A lot of times they say it's due to hit black. The ball doesn't know that it hit black. Still, the next time it still has a 50% chance of hitting black or red. Okay? It doesn't know any different. Okay? So it doesn't know the previous outcomes. That's not going to change the probability of what happens next. Okay? So that would be independent events. So if P of A given B equals P of A given not B, so that's what we looked at, right? The probability of someone preferring English given that they were female, comparing that to the probability of someone preferring English given that they were not female, aka male. If those were equal, that would tell us that those are independent events. If they were equal, then that means those events are independent. So if our probability for the males had been the same as the probability from the females, or very close, we would have said those were independent. But we saw that they weren't equal. That meant they were dependent. Okay. So the 3 questions that you guys need to answer tonight are pretty much like the last 3 questions that we did on the other side. Okay, you have a data table, and just like yesterday, I'll give you guys the hint that you should find the totals first. Okay. So find those totals first. But you'll be doing just what we did on questions 4, 5, and 6 with the data there about the schools. Okay. Is there anything else you guys need me to clarify for this conditional probability, this idea of independent events, dependent events?